So welcome to the first lecture on advanced algorithms. The subtitle would be Strategies for Dealing with Hard Problems. So this is the theme that we will follow mostly in the course. What to do if a problem is hard. You already know what NP-complete is from some elementary course on algorithms and complexity, most probably. Maybe you've seen that comic before. Who has? Who's seen it before? In the book or somewhere on the web? Okay, never mind. So this, you know this book, Gary Johnson, 79, that's maybe the classic treatise on NP completeness. And in the introduction, they have this comic. So what you had before is it's great if you show that a problem is NP complete, because then you're not the only one who couldn't solve it. But in the same book, they go on to say that this is not the end of the story. You just neatly sidestep potential charges of incompetence by proving that this problem is NP-complete, fine. However, the problem refused to vanish at the sound of these mighty words. So we still want to solve it. And just because we know that it's hard doesn't mean it goes away. So in this course, we will investigate a few tricks that you can still do if a problem is hard. There will not be any easy cheats, because that would be against proven theory, right? Nothing to be expected, but a few things can be done. So let's say we look for loopholes in the theory, in a sense. That allow to do things that seem to be not possible in general, but in certain specific cases. How would that look like? So one thing we'll look at first is pseudo-polynomiality. You might probably have heard about that already. This is something that often looks like it's a polynomial algorithm, but if you look close enough, it's not, because the problem is NP-complete. That's not surprising. But that's a typical theme of algorithms that might be fast enough in practice for certain instances, but not for all. We can generalize this to something called parametrized complexity. And there the idea is, in pseudo-polynomial algorithms, the catch is that the input size is one thing, but the values that you can encode in that size might be exponentially larger. So if you encode a number in binary, you have a certain number of bits, and 2 to that number is the largest value you can represent. So if your algorithm is polynomial in that value, it's still exponential. So there's something in the input that's harmful. That's the large numbers. In parametrized complexity, okay, so you turn it around. In pseudo-polynomial algorithms, you're fine. The algorithm is fast if all the numbers are small. There might be many numbers, but if each individual number is small, then the algorithm is still efficient. So there's a parameter, namely the largest value in the input that you have. And if that parameter is small, then the whole algorithm is fast enough. In parameterized complexity, you make this parameter more explicit and allow different things. And if you find a parameter that's typically small for the inputs that you're dealing with, then you might find an algorithm that's exponential in general, but efficient enough for small parameters. Okay, we'll do that in detail in a few weeks. Maybe 1 week. We'll see. Other ideas, so these both solve the problem exactly. We can also compromise on the solution quality. So we'll talk a bit about approximation algorithms. So these are algorithms that don't compute an optimal solution, That's in the realm of optimization problems. The other two are also possible for decision problems. Approximation algorithms don't make much sense for decision problems. But mostly we'll deal with optimization problems, and approximation algorithms don't compute an optimal solution, but one that's at least in a certain range of the optimum that we can prove a bound on that, on the quality. Another thing we can do is randomization. And we'll also see quite a bunch of examples for that. So randomized algorithms might either just use randomness to speed up computation, or they might not always compute a feasible or even the correct solution. So they might even, for a decision problem, sometimes say yes and it's no, or vice versa, but only with a certain small probability. And we will see that for the good cases, we can just repeat the algorithm a few times, and then it's very unlikely that it will still be incorrect. But the possibility is there, and it's a bit strange at first sight to rely on something like this. But in practice, it's not a problem, because it's usually more likely that some part of the hardware breaks. There's a few more things that you can do. For example, you can just say the assumption of the theory in general that you look at worst case inputs is not the right thing in practice. And one such model is called smoothed analysis. That's essentially an idea that was invented for the simplex algorithm. You might know there's the default algorithm for solving linear programs is the simplex method. And in general, it's exponential. But if you add a small error to the input, to the numbers in your LP, then if you add just a tiny bit of errors, then the exponential inputs go away. So it's just very tiny spikes of inputs where you have this exponential behavior. So that's why in practice you almost never see it explode. And the other thing, which in our group I have to mention, is this average case analysis. Simply assuming a worst case might be not so interesting. So smoothed analysis is, in a sense, a stricter version, or it's a different version of average case analysis with a very specific input distribution, in a sense. But we will not go into detail here, because these don't provide new algorithms. But rather they have a more specific look at existing algorithms. But the main theme of the course here will be what can we do to devise new algorithms that don't look like they would solve the complete problem, but in some sense they still solve it well enough. What we'll also not look at is different types of computation, like quantum computing. It's still not clear whether that's practical or whether it will be practical in a few decades or not. And also the theory is maybe not ripe yet. We'll not cover that in the course. I'll just put a question mark here. There's a few other things like DNA computing and stuff like that. It's also promising things, but maybe not ripe yet for a course like this. So the first thing we're looking at is the classic complexity classes, just to make sure that everyone is on the same level and that we have a proper definition in mind when we consider the variations of the theory. And the first thing I want to talk about is the model of computation. So what you probably know is, or maybe just to motivate that before we start with Turing machines and all the details here. The main problem is that our actual machines is always something finite. The memory is finite, the input sizes that you can store or look at are finite, and in a sense also the time that you're allowing your machine to take is finite because you are finite. Right? So the last one is maybe the least problematic, but in practice it is. On the other hand, so this is one thing, but in theory, we want asymptotic statements. Well, let's say we need asymptotic statements. Because on one hand, they abstract nicely from details that are not so relevant. This is especially helpful if you try to understand why a certain algorithm is faster than another. It might be important to know which parts are executed most often because they will give the most contribution. Of course, if your inputs are always very, very small, the picture might be skewed or you might get a wrong impression. But then again, if your inputs are always small, maybe you don't need a fancy algorithm and look at it into detail anyway. So it's usually helpful to know which parts are most relevant in a certain algorithm. Then also, asymptotic statements make the precise analysis feasible in the first place. It might well be that you're just not able to compute anything or prove any bounds for all input sizes, but maybe just for, in an asymptotic sense, for large enough inputs, as we usually say. And then, again, if you have several different algorithms, asymptotic statements allow a conclusive comparison. So if I have different algorithms for the same task, if I say asymptotic, I'm not necessarily referring to the big O classes, because it might, for this last point, it might not quite be true that you can conclusively compare two algorithms that are in the same big O class. And big O, maybe big theta, asymptotic just means that it's some statement that holds for large enough n only. And these can also be more precise than big O. They can be very precise up to a certain error term. So you might want to go to a different course for more details on that. But if you're always looking at all different sizes, you might usually have the situation that for some sizes, one algorithm is better, for another the other one. And in theory, you want to say which one is asymptotically better. Now the problem is, if we want to do asymptotics, then we have to generalize this finite machine that we have to some model of reality that scales with the input size. And we have many different possibilities how to do that. The good news for this course is that it basically doesn't matter too much, because we have what's called the extended Church-Turing thesis. Which in a sense says that any realistic, and this means such a machine could be built, any realistic model of computation can be simulated with only a certain overhead, but only polynomial overhead. On a Turing machine. Now, only polynomial overhead is for a practitioner a bit difficult, but in terms of the theory that we're going to look at, you know that polynomial factors won't matter, won't make a difference. So if we don't know which model to look at, go back to Turing machines. That brings me to this definition. So now things, in the first part of this, in this first chapter, we'll formalize a lot of problems and computational models just to have a solid background. That's not to say that we always go at this level of detail if we prove things. But in case you have doubt on some argumentation, you should be able to get down to some definition that's formal. So here's our definition of time and space, not in a physical sense. So we have two alphabets, which is just finite sets of symbols. Can be anything, just finite. And an algorithm is a mapping from words of the one alphabet to words over the other. So in a sense, all we look at are string algorithms, right? Because we are looking at Turing machines, it's not any restriction because Turing machines always do that. Now time is the logarithmic time complexity, and space is the logarithmic space complexity of that algorithm on a certain input. Now what's meant by logarithmic time complexity? So we have two options. We can essentially choose between two well-established models in theory. One is the uniform cost model. And the other is the logarithmic one. And I just briefly want to argue why the uniform model doesn't make too much sense in general, and give you a brief overview of how to merge both of these in a joint unified model. So the uniform cost model says all arithmetic operations like additions, multiplications, etc. take constant time. And by all, I mean no matter how large the numbers are. Whereas the logarithmic model the costs are proportional to the length of the involved numbers in a sensible encoding. And unless we have reason to change that, we use binary numbers. And the size of the numbers here means input and output. So you know, if you multiply two numbers, the product might be twice as long as the individual numbers. So in that case, you also have to take that into account. So why does the uniform cost model not make too much sense? Well, in the uniform model, you could iteratively set a value to the square of itself. And if you keep doing that, you get extremely large numbers very quickly. And any sensible machine would at least need the time to write out all these bits. But the uniform cost model says, oh, it's constant time, great. That's maybe an indication that this model is not very realistic. if we go back to the Church-Turing thesis, any realistic model of computation, what does a Turing machine do? The Turing machine is always the logarithmic model. Because in a Turing machine we fix the machine, which means we fix the input alphabet size for all inputs of all sizes. That means the alphabet size cannot depend on the input size. So therefore we will stick with the logarithmic model. Now I promised you that there's also a model that unifies the two. Okay. Yep. And this is the word RAM model. I just want to briefly mention it because it's something that I've always found a bit strange. We have these two models that seem like two extremes, but they essentially consider the same thing, numbers and operations on numbers. Why is there just the two and not something in between or something else? Both models have their merits. So in practice, we typically have two regimes. So within practice, I mean if you program, then you either have inputs that fit in an int, fit in one word of your machine. In that case, the uniform model is quite adequate because it's true that in O of one time you can do add, you can multiply numbers, and you can do bit tricks. What exactly that means depends a bit on the machine, but you can do bitwise AND of two words. You can do OR and XOR and some more sophisticated things. And you might even have machines where a word can be a bit larger than the usual word. You could have SIMD instructions where you have up to 256 bits or something representing a whole vector of integers. And you can take this whole vector and add it to another vector. In all these cases, the unit cost model is what you have. But if the numbers are larger, then you have to use some library that gives you access to arbitrary precision integers or decimals. So you might, in Java, you might use big integer. In case you never used that, it's a bit clumsy to use because you don't have operator overloading in Java, but in a sense it's you use it like it would be in normal numbers, but it's pretty slow. There's usually a large gap between the two. And the point is that these essentially store numbers as strings. Which is, in a sense, the only thing you can do. And then you have the logarithmic model. Now, word RAM, the unified model says, let the word size, so that's the number of bits in one word, let this depend on the input size. It doesn't sound very realistic at first because the machine seems something fixed and the input is growing. But actually, if you look at historical data, then the word size has grown. And if you even compare it with the input sizes, it's not so far-fetched. Now the point is, what functions for W of n make sense? And a good assumption is that it's logarithmic. If it's much bigger than that, then you can fit many, many things into one word and you can do all kinds of trickery. If it's much smaller than that, then you get already problems if the input is just a vector or an array of numbers. You would at least want to fit this into main memory, right? And then to be able to address each cell in the input would at least mean that the words that you use as address in your computer should be large enough to hold so many different values, which is just log n in that case, right? Does that make sense? Now the interesting thing is, even on such a machine, because you can do bit tricks and you can do some clever case distinctions and so on, it's not the same as the logarithmic model if you don't allow the bit tricks. It's not the same as a Turing machine because you can, with that assumption, sort n words, so n integers that fit into one word, in n log n time. So it's definitely not comparison based in the classic sense, but you have to do some tricks. We won't go into detail here. It's a bit involved, but I find this kind of remarkable that with this generalized model you get some interesting new results. Okay. Back to this course. So for us, we're not so much interested into log factors. We're distinguishing polynomial and exponential, so this won't make a difference. We've already defined that we will stick to the logarithmic model, which means essentially we stick to Turing machines. Now it's up to now we only defined it on a specific input, but of course you know this. We usually just look at the worst case. So in the formal model, that means we have an algorithm A that computes a mapping as before, and then the input size is simply here the length of the encoding of the input. That's also what you need, what you know, but stress it once more. And then you take the maximum over all inputs of that size as your worst case time. So note that here you have an n and here you have an x. So it's an overloaded function with different types. It's maybe not the nicest notation, but we won't ever need that again, so just stick to that one. And the same thing for space. Okay, up to now, an algorithm was just some mapping of words to words. But in complexity theory, we are interested in specific algorithms, namely those that decide a decision problem. So what's a decision problem? Theoretical computer science likes to define things as tuples. So here's the tuple for a decision problem. What's the components? So we fix an alphabet as before, just to be specific. Usually that's not very important. Then we have a universe of things that we are allowed to input, and then there's a language. Now in the sense of formal languages, this is a language that's a subset of U. That's the instances that we would like to recognize. Okay? So the decision problem is essentially given an x in U, tell me whether it's in L or not. Right? As it's written here, often we have U is just the all language, but sometimes it's convenient to allow subsets. So for example, we will have in a second the problem sat, where you encode formulas as words, and it's very convenient to allow that certain words don't represent a valid formula. They're just not syntactically correct. Okay. Nothing new, I guess. Okay, here's an intriguing result that we won't go into detail and won't prove, but there's certain decision problems where you can't order algorithms, or where you can't even define what's the best algorithm, because there's a decision problem that whenever you take a specific algorithm that solves the problem, there's another one that's much better, namely a logarithm of the cost of the other for many numbers. It doesn't say for all numbers greater than an n0. That would be amazing. That's not the case. But for an infinite number, so it's impossible to define the best algorithm for such a problem without specifying the n as well. So simply saying the complexity of a problem is the running time of the best algorithm for it won't work. Okay? That's all that this is saying. So the way out is we only consider bounds. If U is a problem, decision problem, for example, then we say that O of G of n is an upper bound for the complexity of the problem. So we are not talking about specific algorithms, but we want to say something about the complexity of the problem itself, right? So it's an upper bound if there is some algorithm that uses at least this. So the problem can't be more complex than a certain bound if I can solve it in that time. And for a lower bound, we have to work a bit harder. So the complexity of U is at least f if every algorithm that solves the problem has this time bound. So that's why upper bounds are usually relatively easy. You just find some algorithm. It might be not so easy to argue why you can't do much better, but for lower bounds, you always have to show something about all algorithms, which is, of course, much harder. And we call an algorithm optimal if it's in theta of a lower bound, in a sense. So we can't do strictly better in terms of O calculus. Of course, optimal is still leaves a lot of slack, so there's still a constant that we don't consider, and so on, and it's only asymptotic. But for this lecture, this is the definition of optimal. And it's also a pretty common definition in algorithms. Okay. So now, just to briefly state that again before we start with that. So we now defined the formal setting, what's an algorithm and what is time complexity and so on. The goals of complexity theory are to formally specify, so in a sense define, what problems are practically solvable. And you know that we'll define polynomial time as practically solvable. And the second goal is to devise methods to classify problems into solvable and unsolvable ones in terms of practically solvable, right? So maybe write into tractable and intractable ones. And as we'll see, the intractable ones will not be full mathematical proofs, but rely on the famous conjecture P not equal NP. But what's P and NP? So this is also something you probably know from the algorithms class, but here again, the formal definition of P and a tractable algorithm is any language for which we have a Turing machine M, for which the time is in O of n to the c, so bounded by some polynomial. And it must be a Turing machine that's deterministic, unless we state it differently and explicitly write non-deterministic, we mean deterministic Turing machines. And the set of all such languages L for which we have such a machine is the class P. And we call a language in P tractable or efficiently decidable, well knowing that this is kind of a theoretical definition. But it's a good definition still because it's robust against changes in the computational model. Because as we've seen before, so that was the extended Church-Turing thesis. All reasonable models can be simulated on a Turing machine with only a polynomial overhead. And that means the class P will not change if we go to a different computational model, if it's one of these realistic ones, whatever that means. Also, unless this C, this exponent here, is too large, such algorithms are indeed practical. I write usually because there's examples of algorithms that are even linear but still usually don't finish. We're now beaten by theoretically worse ones, but these are exceptions. So the example that I'm referring to is a check for planarity in graphs that's notorious for having extremely large constants hidden in the O. So even though it's linear in the input size, it's essentially not practical. But these are the exceptions. Most algorithms are not such beasts that try to fool theory, but usually if you have a small exponent in the polynomial, it's practical for reasonable input sizes. And another reason maybe why this is true is that polynomials have the property that if you double the input size, if you go from n to 2n, okay, adds a factor is strange, only gives us a fixed factor more in running time. So again, this fixed factor depends on the c. I mean, how to prove this? Just insert, and then you see that 2 to the c is kind of this factor that you get, which might be large if c is not very small, but still it's a fixed factor that you pay more whenever you double the size of the input. And doubling the input size is already something that doesn't happen too often in practice, right? Whereas exponential is, of course, different. There you add something and you get this constant factor. And adding something you can do a lot. You can do often in practice. Okay. So that page won't be much. But still, so how do you show that the problem is in P? That's simple. Find some algorithm that's polynomial. and solves the problem. Okay, maybe sometimes it's not so simple, but as a method it's simple. Oops, okay. Now here I can start using this abbreviation that you might know, polytime, which stands for polynomially bounded time. If you want to be strict, you should also add in the length of the encoding of the input in a sensible encoding, and so on and so forth, right? There's quite a lot hidden into these small words that we don't want to repeat over and over again. So whenever I write polytime, I actually mean all these things, and you're responsible for keeping that in mind. Sounds great. Okay. If you find such an algorithm that solves the problem, you're done. For some problems, good luck, but still, it's easy on a conceptual level. Now assume you don't find an algorithm. Now you show that it's not in P. Up to now, we don't have a good method for that. But of course, there is one. I inserted the page at the wrong place. Okay, that's going to be a mess in the lecture notes. Anyway, here's the right definition. There's the class NP, and we'll talk in a second about how to prove that something is probably not in P, but we need a few definitions before we come back to that. So a Turing machine can also be non-deterministic. We won't define what actually is meant by this in very much detail, but the idea is that at any point in time, the machine can make one of a finite number of different choices, and depending on these choices, the computation can take different paths. So a computation is not just from one point to the end, and then you say yes or no, but you can have branching behavior at every single point. So you get a whole tree of possible computations. And if one of these says yes, then the whole computation accepts the input. But if all of those say no, then the machine rejects the input. Now the time complexity is a bit more involved in this case because we have many branches and some might even not terminate. So we define the time complexity as the length of the shortest accepting computation. So we might also have several of these branches that say yes, and one might be much, much further down. We only take the shortest one. And as before, we take the worst case over all inputs of a certain size n. That's just as before. Now only with the restriction here that m can be non-deterministic. Then the class NP is simply as before, it's the set of all languages, so that we have a machine that runs in polynomial time, but this time it's non-deterministic. And that's, of course, what NP stands for, non-deterministic polynomial time. So this sounds like a very, very strange class of problems, right? Non-determinism is a very unintuitive thing. So therefore, people usually try to not work with that definition, but rather with this one, which also defines a class of problems, VP, by means of verifiers, and we'll show in a second that they're the same. Often people completely skip the Turing machine definition. But that definition has the clear advantage that you can prove Cook's theorem, as we'll see in a couple of slides, maybe today. We'll see. Okay, what's this class VP? We still have an algorithm, but now it's not only given an input, an instance of the problem, but also a certain mysterious string that we will call certificate later. And this algorithm is a verifier for this language L that we fixed before. If the following is true, there is some certificate C so that A with the input and that certificate accepts, returns yes. So the 1 is a yes, maybe nicer. For all other certificates, for all other inputs here where this is not the right certificate, it may do whatever it likes, probably reject the input. But if I guess the right certificate, then this is accepted by the algorithm. Now the important thing is that this algorithm here is polynomial time and deterministic. It's not a non-deterministic Turing machine, it's just an algorithm by which, in a formal sense, we always mean a deterministic Turing machine. But again, by the extended Church-Turing thesis, we know we could also allow some more convenient model like word RAMs or something like this, or even more sloppy pseudocode as we'll do later. Right? So it's an ordinary algorithm in the sense that it doesn't use any kind of magic guessing and non-determinism, but it gets this mysterious certificate. Now the class VP is defined as the languages that are accepted by these verifiers. So it's all languages so that we can find a verifier which only has to accept an input if it's also given the right certificate. Right? So VP is the verifiable in polynomial time class. And you might want to see an example. That's the basic one, the mother of all decision problems, SAT, the satisfiability of propositional logic. So we're given a Boolean formula. Phi. And the question is phi satisfiable? Now in a formal sense, we should specify what the encoding alphabet is and what formulas look like. And then we can say that the language SAT is the encodings of all the formulas that correspond to the encoding of all satisfiable formulas. But I guess we can skip that. So just, I mean, what would be a sensible encoding for formulas? You would say they have variables x1 to xn, which we can encode by a specific symbol signifying no comes a variable, then the binary number of the variable, some log n bits, and then we can have the usual symbols from propositional logic as additional symbols. And we just use a string representation of the formula as you would write it as a representation. It might not be the most convenient for a Turing machine to work with, but we don't really care. Because we know that we can essentially parse it into a tree and then work on it somewhat conveniently. But this is a level of detail that we usually skip in this lecture. And I think you agree that this is a good decision to not go into this detail. Now we have two different definitions that at first sight look very different, but they define the same class of problems. You might have seen this proof before, but maybe not, and it's insightful to see it in a bit of a detail, even though it's not very complicated. So I'll try to not do it too quickly. I have to show two inclusions. Let's do this one first. So we have some language in NP, which means it's a language that's accepted by a non-deterministic Turing machine. So that's the language of the machine is just L. Now we have to construct a verifier for this language. And it's up to us to design how the certificates work, right? So the definition of VP just requires that there is a certificate so that a certain verifier works. But it's up to us to design one. So if this is an input for the verifier, so X is a word of the language, or maybe not, we want to check that. And the certificate is a binary string, that's how we defined it. Then our verifier A essentially simulates the Turing machine. But because the machine is non-deterministic, we have to know which path to take in the computation tree. And so we take C as guide through the non-deterministic choices. So in general, a Turing machine might in every step take one of a finite number of different paths. Okay? Then we just take a certain number of bits from the certificate until we have decided which of these M paths we take. So something like this, bits from C tell us which path to take. In terms of Turing machines, the paths would be the transitions, right? So you have this transition relation given the current state and the current symbol that you have on your tape. You have a certain number of different moves that you can do in that state and with that symbol, and the number of the next states that you can go to and the symbols you can write is M. Then you can take just not one but several bits, and then you know which one to take. I guess it's easy enough, even though it's a bit fiddly because we don't have memory strings but binary, but it doesn't make a big difference. Okay? So that means with a given C, we simulate exactly one possible computation of the non-deterministic machine. And we know if the machine in the end accepts the given input. So that's an if and only if, of course. If and only if one computation accepts And that means the C that corresponds to the choices that lead to this computation is our certificate. Okay, so the certificate that was very abstract in the definition in the first place has a very specific meaning, actually, because it just says us which guesses to make. There are a number of corner cases. We might consume all of our certificate before we reach the end of the computation of M, so we might have to make more non-deterministic cases. In that case, just reject. That can't be the right certificate. Well, if we've finished and there's part of the certificate left, that's not a problem. It depends on the holding state. If the machine stops in an accepting state, then we accept, otherwise not. So that was the one inclusion. I guess we are convinced that this verifier A accepts exactly this, or verifies exactly this language. Now the other inclusion. Now we are given a verifier, and we construct a Turing machine. So let's call it again A, so that A verifies the language L. Now we construct, conceptually, a non-deterministic Turing machine. Which basically does two things. So first, M generates non-deterministically a binary string C. Now we should know how long this string can be, but we know that for a verifier here, so I should have written that this is a polytime verifier, right? And that means if its running time is bounded by a certain polynomial, also the certificates are bounded by a polynomial, because it can't even look at more bits if it doesn't have more time, right? So there's a certain polynomial that bounds the length of the C, and that's fixed for the given verifier. So even though it's non-constructive, we don't know what the polynomial is. There is one, and for every verifier there exists a machine, as we will show, even though we can't really construct it. It's a kind of non-constructive proof, even though we say construct a non-deterministic Turing machine. So with P of length of x bits, x is of course the input that the machine or the verifier get. In this case, it's for the machine, so, and P is the bound on the running time for the verifier that we are given. Well, now we've guessed a certificate, maybe it is one, so just simulate or run this as a subroutine, as you like, A of x with this random string. And then copy the output of A, right? So if A accepts with this certificate, then we were lucky in guessing. Otherwise, we were not lucky, but we know if there is a valid certificate so that A accepts, which has to be the case when X is in the language, then one of the non-deterministic computations will guess this very specific C, and we will accept. Even though that's just one computation, that's sufficient. That was the definition of acceptance. Okay? Well, and vice versa. I mean, if X is not in the language, then there's no certificate so that we accept. And then we won't accept here. So the language of the machine that we constructed is just the same as that verified by A. And that completes the proof. Okay. Before we go on, let me add a little remark. So did that go to the wrong place again? No. We already have seen different types of problems, and this will be something that we extend during the lecture several times. So I'll start it here, even though it's not yet very confusing. We have two different types of problems. So the original NP definition says we have languages, right? So this is the same for VP, as we know. It's languages, which means decision problems. A word can be in the language or not. And that was fine for Turing machines. That was fine for verifiers. So decision or yes-no problems, if you like that better. But in many cases, what we are interested in practice is not really the decision version, but a slightly different one. And especially the certificate point of view says that these problems have more structure than just yes-no, but rather we can define that a variant of the problem is a certificate search problem. We're not only asking, is this part of the language or not? So we're still asking the yes-no question. But in case of a yes, we want to see a witness. We want to see proof of the answer. In case of a no, we don't. You know that this is the great asymmetry in NP. And there's the mirror image co-NP where you have to verify the no instances. But it's a different problem to only ask for yes, no, or also to ask for a proof if yes is the answer. And often this is much more interesting. So as an example, we have seen that satisfiability problem is one of these problems that fits into our regime. But often we are not only interested in the satisfiability yes, no, but we want to see a satisfying assignment of the variables, right? So yes, no is phi satisfiable. And if so, what is a satisfying assignment? So it's obvious by definition that if you can solve the search problem, you can also solve the decision problem. Just throw away the certificate. An interesting question is, if you can solve this decision problem, can you also solve the search problem? That's so should write it down. Whenever we can solve the decision problem. Oh no. There's an easy answer. In some sense, yes, because if we apply the Turing machine definition, then the decision problem is decided by a non-deterministic Turing machine. And if we accept that as an algorithm, we could just make that Turing machine store its decisions and output them, right? So it can not only say, yes, I accept, it can say, yes, I accept, and this is the path that made me accept. So it's easier for you to verify that this is the correct outcome. But this is a certificate that doesn't have a specific meaning, not necessarily. We don't know whether a non-deterministic Turing machine for SAT really chooses an assignment for the variables. Probably it does. I can't imagine how to do it differently, but only from the existence of some machine we can't extract the assignment. So that's the problem. So we get some kind of certificate, but we don't necessarily get the search problem in the way that we want to specify it in practice. Specifically, if we fix a model, so if we only allow to reuse, if you only allow black box reuse of a decider. So assume we have some problem that decides the yes-no question, but doesn't tell us something about the certificate. It's not so clear in general whether we can also reconstruct the search problem's witness that we would like. So for SAT, if we have a problem that only tells us if a formula is satisfiable or not, it's not in principle clear that we can compute an assignment. For the specific problem of SAT, we will show in the exercises that it's actually easy to do. But as far as I know, and I've consulted a few books, there's no general construction how to get a certificate with a meaning just from the decider. But for any specific problem you look at, it's usually easy. It's a bit intriguing. Okay, so we've already seen two types of problems, the decision version and the search version. Okay, I will not yet talk about the reductions in general. Now let's first do it for the decision problems as usual. So the overarching theme was still complexity theory wants to tell us which problems are hard and which are easy, and we want to have proof methods to distinguish the two. And we still haven't seen those. Now, to show that a problem is probably not easy, probably not tractable, we use the following. The idea of a polynomial time reduction, which I again abbreviate as polytime reduction, is that we have two languages, and then we have an algorithm, so again deterministic and again polytime, that computes for every instance of and every potential member of the one family, one of the other alphabet, so that if one is in the language, then the transformed version is in the other language. if and only if. So that's the usual notion of reduction. It's the strict one, the many one reduction, where you only apply one times the reduction, and then essentially you call the method for the other language, and you have to accept the answer without changing it. So you might know that there's different types of reductions that differ a bit in the nuances. In the distinction between P and NP, they don't differ usually. But this is the version that you have to use if you want to make a distinction between NP and co-NP. That's why we stick to this. So you apply once a function to your input, and then it has to be an instance for another problem. And if the original was a yes instance, then the transformed one must be a yes instance, and vice versa. We'll see examples, and you'll do examples in the exercises. Now, the central notion is that of NP-hard and NP-complete problems. A language is NP-hard if every other language in NP can be reduced to that language. So I should maybe add that this less or equal is best thought of that L2 is more complex than L1. And that way you can just read it as an ordinary order relation. And that's exactly what it says, because more complex, that means whenever you solve the tougher problem, the L2 problem, you also have an algorithm to solve L1, to decide L1. Because if you have such an algorithm for L2, you can use the transformation to decide L1 as well. So that would formally be the next lemma, essentially, which we'll prove in a second. I should also say NP-complete, what that is. That's NP-hard plus the language is itself in NP. NP-hard doesn't make that assumption. NP-hard just says for all languages in NP, we have this relation. But it doesn't say that L itself is in NP, but for all our problems that we will study, we'll actually have that. So NP-complete is the notion that we usually aim for. Now here's why NP-hard problems are the interesting ones. That's the last thing that we're going to do for today. If a language is NP-hard and it is in P as well, then P and NP must be the same. So what this means is if you can show for any of the NP-hard problems, which we haven't talked about yet whether they exist at all, but you might know that they do. So if for any of the NP-hard problems we can show that it is in P, so we can efficiently solve any of these, then we have an efficient algorithm for all of them because they all lie in NP. They all lie in P then. So let's quickly prove that. So assume L is NP-hard. And also L is in P. That means if it's in P, that means we have a deterministic algorithm. An algorithm that decides this, or you can write a Turing machine. The other way around. So we have a Turing machine M, so that the language of that machine is just our L. Now for any u in NP, we know by NP-hard that P is at least as complex as u. So there's this reduction. Let's again write it as deterministic polytime algorithm B, so that whenever an instance of u is a yes instance, if I transform the instance with B, then it's in L. And now we have to show that, for showing this equality, we have to show that any language in NP also has a deterministic polytime algorithm that decides it. So suffices to show that there's an algorithm to decide u in polytime. And we just construct that. So C does the following. It computes, so it calls B on X. If you want to insist on Turing machines, then we simulate the Turing machine B. And then return whatever M of B of X does, again by simulation. So this has an outcome, it accepts or it doesn't. So it accepts if and only if B of X was in L, which was if and only if X was in U, so ordinary U. So C decides whether X is in U in polytime, because B is a polytime algorithm, deterministic, M is deterministic polytime, so the whole thing is in polytime. Okay, so if we have one of these NP-hard problems, and we have reason to believe that this is wrong, then by contraposition, we have to assume that this language is not in P. So we probably have this separation. Okay. If we have a language that's NP-hard, it is probably not tractable. And the open question for today is, does this exist? I mean, you might, so you already know this part of the theory, so it's not a big surprise for you, but actually this notion of NP-hardness is pretty sophisticated. Every problem in NP should be transformable to such a thing. So we know how to do it and how this turns out, but it's actually a pretty mighty thing, and it could just have been that it doesn't even exist, right? But that's the topic for the next time.